I would like to present our work on making the most out of deep networks when trying to model 3D surfaces as triangulated meshes. Of course, this begs the question of why we would want to use meshes, given that there are many kinds of surface representations that may be easier to incorporate into a deep learning pipeline. Surfaces can be voxelized, represented by point clouds or by triangulated meshes. All these representations have their pluses and minuses, but triangulated meshes are particularly well suited when we need to represent high-frequency details, which is one of the reasons they have been so popular for so long. This is definitely the case in computer graphics when accurate renderings are required. This is also true in biomedical imaging when we need to compute the surface areas of specific structures, or in computational fluid dynamics when we want to represent boundary conditions. Unfortunately, it is not obvious how to design and train a deep network to produce such meshes with arbitrary numbers of vertices in topology. This is the problem I would like to address in this talk. The Pix2Mesh algorithm that was presented at ICCV last year was designed with this purpose in mind. It starts from an image and outputs a mesh. In our own work, we have extended it to take a volume as input instead. In both cases, the input is encoded into a latent representation and then decoded into a mesh. This gives good results, but they can be further improved by using a two-stream architecture that decodes both to a mesh and to a volumetric representation, with intermediate connections between the two decoder streams to ensure they truly operate in tandem. These three examples feature CT, MRI, and EM data volumes. In all three cases, our approach yields smooth surfaces with far fewer artifacts than UNet, with or without post-processing, which we use as a baseline. This is a step in the right direction, but this approach still relies on deforming an initially spherical shape and can therefore not handle topology changes. It has long been known that a natural way to do so is to use an implicit surface representation instead of an explicit one. And last year, deep signed fields, or SDFs, have emerged as a great tool to harness the power of implicit surfaces in the deep learning context. This has generated an enormous amount of interest, and I'd like to briefly summarize how SDFs work before presenting our own use of them. A volumetric SDF is a function from R3 into R that assigns to a point X a value that is assigned distant to the surface. Their great strength is that the zero crossings of the surface can change topology while the function itself changes continuously and differentiably. Until recently, their perceived limitation was that storing the value of a 3D function was so memory intensive that surfaces could only be modeled at very low resolutions. That perception was changed last year by one key insight. There is no need to store the values of the SDF explicitly. A deep network, denoted as f theta here, can be trained to estimate its value at any point instead. This means that the target surface can be sampled at any resolution. Furthermore, the deep network can take as input, in addition to the point X, a code C that conditions its behavior. As a result, changing C, changing the surface shape, and C becomes de facto a low-dimensional latent vector that can parameterize the surface, and this parameterization is differentiable. However, one bottleneck remains. If an explicit surface representation is required, one has to use a Marching Cube algorithm, which is not differentiable and makes it difficult to incorporate this representation into an end-to-end trainable pipeline. To see where the problem lies, let us consider a loss function L that depends on the vertices and facets of a 3D triangulation, and let us assume that the surface it represents is parameterized implicitly by a network f theta, like the one we presented in the previous slide. To compute V and F, we can run a marching cube algorithm, which is fine during the forward pass. However, we cannot easily compute the gradient of L during the backward pass because the output of marching cubes is not differentiable. To do it, we must instead exploit an important property of sign distance functions. Given a true distance function, S, and an infinitesimal perturbation delta S of it, a point on the surface will move in direction normal to the surface, which is also the gradient of S. We can therefore prove that the derivative of a vertex location is the gradient of S at that location. And since f theta closely approximates a sign distance function, for each vertex, we can approximate the derivative of dv over df by the gradient of f, which makes the whole loss differentiable. Because the loss is now differentiable, we can minimizing using a gradient-based technique. This enables us to start from the sphere on the left side and turn it into the torus on the right. At each iteration, we start with a code C, use the marching cube algorithm to compute the vertices, use them to perform the forward and backward pass as discussed, and finally, take a gradient step and iterate. In this scheme, the non-differentiability of marching cube becomes irrelevant because it is only used to compute surface samples. I would now like to show how this works in practice on two different applications. First, single view reconstruction, and then shape optimization. Given a set of 3D shapes, such as those from the ShapeNet or Pic3D datasets, we can train a ResNet 50 to extract codes from rendered images of these shapes. The resulting codes then become inputs to the SDF f theta, which has been trained to regress the 3D shapes. A previously unseen image containing a target object can be fed to the encoder, resulting in an initial code C that is decoded into a 3D shape that roughly matches the object outline. We can then exploit the differentiability of the loss function to refine C and maximize the overlap between the 3D predicted shape's projection and the true object outline. We feed as input to the encoder an image I of a chair from the Pic3D dataset. The encoder returns a code C0, which decodes the rough shape to the right of I. We then optimize C to maximize the overlap between the real chair and the projection of the predict one. The final result on the right is an accurate model. And as can now be seen at the bottom of the slide on two additional examples, our reconstructions tend to be more accurate than those of earlier methods. Let us now turn to our second application, shape design, which, unlike single view reconstruction, is directly applicable in an industrial context. In current practice, the typical way to optimize the aerodynamics of a vehicle, such as the car shown here, is to build a 3D mesh model and then to run a CAD simulator. If the results are not what was hoped for, which is often the case, the model is modified and the simulation rerun. This clearly works. Our cars move and our planes fly, but it is slow in large part because running each individual simulation takes a lot of time, and so does redesigning the models. One way to address this difficulty is to use what's known as a surrogate method. One runs a number of simulations on a training database of shapes, such as those shown here. On this slide, the colors represent pressure fields that can be used to estimate drag. The resulting pairs of shapes and associated drags can then be used to train a regressor to be used to predict the drag of previously unseen shapes at a much lower computational cost. This makes it possible to effectively explore the shape space and find the lowest drag shape. In our own work, we use a geodesic CNN for this purpose. As can be seen in this slide, the simulated result and the predicted ones are very close. Furthermore, predicted results are differentiable, which makes gradient-based optimization possible. To impose the right kind of priors on the shape space we want to explore, we couple our drag estimator D to the f theta function we introduced before. This yields a differentiable function that takes a code C as input and returns the drag D of C associated to the 3D shape S defined by C. To refine an initial car shape, we therefore use our encoder to generate an initial value of C. We then minimize D of C under the constraint that enough space must be left for the engine and passenger compartment. In this way, a pickup truck can automatically acquire a much more aerodynamic shape. And here is another example. We could, of course, have used a different parameterization of the initial shape to perform the drag minimization, and we tried. On comparative tests on the ShapeNet cars, ours performs on average noticeably better than its competitors. Occasionally, it even changes the topology of the initial shape, for example, by removing useless spoilers. In short, we have shown two important results. First, combining implicit and explicit surfaces at an early stage of a deep net architecture is beneficial. Second, deep sign function can be used to represent explicit surfaces while preserving end-to-end differentiability. As we have seen, this is readily applicable in the field of computer-aided design, and we hope that it will also open the doors to new applications in many other fields. Finally, I would like to thank all the people whose work I presented today and who are listed on this slide.